Hi, we'll discuss about Laplace transforms in this video. We have already seen that integral transforms are useful tools to solve problems which are difficult to do in a particular domain. What integral transforms does is that it will transform the problem into a transform space where it can be solved by relatively easier techniques, and the solution in the transform space will ultimately be taken back to the original problem space by using an inverse transform. We have discussed about Fourier transforms in the last video, and in this video we'll try to see how Laplace transforms do the trick. So the Laplace transformation method is generally useful for obtaining solutions of linear differential equations, both ordinary and partial. And the advantage is that this technique will reduce differential equation to an algebraic equation, thus avoiding going to the trouble of finding the general solution and then evaluating the arbitrary constants. In addition to that, this technique can be extended to systems of equations and to integral equations, and it often yields results more readily than other techniques. We'll start with the definition of Laplace transform. The Laplace transform L of ft of a function ft is defined by the integral fs equal to Laplace transform of ft, and this is equal to integral 0 to infinite e raised to minus st ft dt. So this is how we define the Laplace transform. And the integral in this equation is a function of the parameter s, and we denote it by fs. Now the function fs is called the Laplace transform of ft. Now the operator L is a linear one. That means that if we have L acting on a superposition of ft and gt, this will be equal to integral 0 to infinite e raised to minus st, then aft plus b gt, then dt. When we expand this, this is integral 0 to infinite e raised to minus st ft dt plus b times integral 0 to infinite e raised to minus st gt dt. And this can be written as a times the Laplace transform of ft plus b times the Laplace transform of gt. Here, a and b are arbitrary constants and gt is an arbitrary function defined for t greater than 0. Now, the inverse Laplace transform of fs is a function ft such that the inverse operator acting on fs will result in the original function ft. And we denote the operation for taking an inverse Laplace transform by the operator L inverse. That is, we operate algebraically with the operators L and L inverse, bringing them from one side of an equation to the other side. We'll now try to do this problem. Find the Laplace transform of ft given by ft equal to 1 for t between 0 and 2 and ft equal to 2 when t greater than 2. By definition, the Laplace transform of ft is equal to integral 0 to infinite e raised to minus st, then ft dt. Now we'll rewrite this as integral 0 to 2, so that is the first limit, e raised to minus st, and within this limit the value of the function is given to be 1, and from limit 2 to infinite the value of the function is given to be 2, and this is multiplied by dt. When we integrate this, this is e raised to minus st over minus s within limits 0 and 2, and the second integral is 2 times. We'll write this as limit b tend to infinite, integral 2 to b, then e raised to minus st times dt. So this can be written as fs equal to e raised to minus 2s over s with a negative sign. So that is the first term, and the second term is 1 by s. So this is the first term in the previous equation after applying the limits. Now the second term in the previous equation becomes 2 times limit b tend to infinite e raised to minus sb over s. Then the second term will be e raised to minus 2s over s. And this is equal to e raised to minus 2s over s plus 1 over s plus 2 times. The first term, when we apply the limit, becomes 0 because e raised to minus sb tend to 0 as b tend to 0 for s greater than 0. And the second term is e raised to minus 2s over s. And when we add the terms, we'll have 1 by s plus e raised to minus 2s over s, which is the required answer. We'll now discuss about the conditions for the existence of Laplace transforms. The Laplace transform ft exists if the function satisfies the following two conditions. The first condition is that ft has to be a piecewise continuous function on every finite interval of t between 0 and capital T. The second condition is that we should be able to find constants m and a such that mod of ft has to be less than or equal to m times e raised to at for t greater than or equal to capital T. And if that condition satisfies, then we say that the Laplace transform of ft exists for s greater than a. A function satisfying condition 2 is said to be of exponential order as t tend to infinite. And these are the sufficient conditions on ft under which we can guarantee the existence of a Laplace transform, that is L of ft. And under these conditions, we can see that the integral converges for s greater than a. That is, if we take integral 0 to t, then ft e raised to minus st dt. We'll take the modulus of this one, and this will be less than or equal to integral 0 to t modulus of ft e raised to minus st dt, and this is less than or equal to integral 0 to t, then ft, its value is m e raised to at, then e raised to minus st dt, and this is m times integral 0 to infinite e raised to minus s minus a t dt, which will be equal to m over s minus a. Thus, we demonstrate the absolute convergence of the integral defining L of ft. Now, note that m over s minus a tend to 0 as s tend to infinity. So that shows that limit s tend to infinite fs. So that is m over s minus a equal to 0 for all functions fs, which is the Laplace transform of ft, such that ft satisfies the conditions 1 and 2 that we have seen previously. Now it follows that if limit s tend to infinite fs is not equal to 0, then fs cannot be the Laplace transform of any function ft. Now we'll discuss more about exponential order. One simple way of determining whether or not a specified function is of exponential order is the following one. If a and b exists such that limit t tend to infinite e raised to minus bt, then mod of ft. If this exists, the function ft is said to be of exponential order, that is of the order of e raised to minus bt. As an example, let us check whether t cube is of exponential order as t tend to infinite. Now, in this case, we'll check whether limit t tend to infinite e raised to minus bt t cube exists. So this is equal to limit t tend to infinite, then t cube over e raised to bt. By a quick inspection, we see that this function does not converge. So we'll use L'Hospital's rule, limit t tend to infinite t cube over e raised to bt, and this is equal to limit t tend to infinite 3t square over b e raised to bt when we differentiate both numerator and the denominator. And in this case also the function does not converge, so we'll again differentiate the numerator and denominator. Limit t tend to infinite 6t over b square e raised to bt, and again performing differentiation of both numerator and denominator. This will be 6 over b cube then e raised to bt. And when we apply the limit, this will be equal to 0. So this indicates that t cube is of exponential order as t tend to infinite. So this is how we check whether a function is of exponential order or not. We'll now try to find the Laplace transform of some elementary functions. The first one is ft equal to 1 for t greater than 0. The Laplace transform of 1 is integral 0 to infinite e raised to minus st multiplied by 1 multiplied by dt, and this is equal to e raised to minus st over minus s from 0 to infinite, and this is e raised to minus infinity over minus s minus e raised to minus 0 times t over s, and this is equal to 1 over s provided s is greater than 0. So Laplace transform of 1 is 1 over s. The second function is t raised to n, where n is a positive integer. Now Laplace transform of t raised to n is equal to integral 0 to infinite e raised to minus st, then t raised to n dt. We'll perform integration by parts. For that, let us take this as u and this as v, or rather v prime. That is the first derivative of v. When we do the integration by parts, this is u v prime dx, which is equal to u times v minus integral u prime v dx. And Laplace transform of t raised to n. So this is equal to first multiplied by integral of second, that is e raised to minus st over s, then the limit 0 to infinite, minus integral of differential of first multiplied by integral of second, e raised to minus st over s minus s times dt. And this will be 0 for t greater than 0 and n greater than 0. Therefore, this turns out to be n over s integral t raised to n minus 1 e raised to minus st dt. The limit 0 to infinite, 0 to infinite. So we have seen that Laplace transform of t raised to n equal to n over s, then Laplace transform of t raised to n minus 1. And when we take the Laplace transform of t raised to n minus 1, this will be equal to n minus 1 over s, then Laplace transform of t raised to n minus 2. When we iterate this process, we'll get Laplace transform of t power n equal to n times n minus 1 times n minus 2, then finally 2 multiplied by 1 over s power n, then Laplace transform of x 0. And this is nothing but Laplace transform of 1, and this is equal to 1 over s. Therefore, this is equal to n factorial over s power n plus 1. So the Laplace transform of t power n is n factorial over s power n plus 1. Now the third example is e raised to at, where a is a real constant. Proceeding as before, we have L e raised to at, and this is equal to integral 0 to infinite e raised to minus st e raised to at dt, and this is equal to integral 0 to infinite e raised to a minus s t dt, and this is equal to e raised to a minus s times t over a minus s from 0 to infinite, and this is equal to 0 minus e raised to 0 over a minus s, and this is equal to 1 over s minus a. So this is the result when we calculate the Laplace transform of e raised to at. Now ft equal to sine at, where a is a real constant. The Laplace transform of sine at, this is equal to integral 0 to infinite e raised to minus st, then sine at dt, and this is equal to integral 0 to infinite e raised to minus st We'll expand sine in terms of the exponential. So this is e raised to iat minus e raised to minus iat over 2I times dt. Now this is equal to 1 over 2I integral 0 to infinite e raised to minus s minus ia times t, and then minus e raised to minus s plus ia t, then dt. When we integrate, this is 1 over 2I e raised to minus s minus ia t over minus s minus ia. So that is the first term. And the second term is minus e raised to minus s plus ia t over minus of s plus ia within the limits 0 to infinite. And this is equal to 1 over 2I, then 1 over s minus ia minus 1 over s plus ia. And this is 1 over 2I s plus ia minus s minus, so that is plus ia divided by s square plus a square, and that is equal to 1 over 2I. Then in the numerator we have 2ia, in the denominator we have s square plus a square. 2I and 2I cancels, and this is equal to a over s square plus a square. So when we calculate the Laplace transform of sine at, that is a over s square plus a square. Similarly, we can show that the Laplace transform of cos at is equal to s over s square plus a square. And similarly, to calculate the Laplace transform of the hyperbolic sine function sin h at, we'll use this substitution. Sin h at equal to e raised to at minus e raised to minus at divided by 2. So this will give us Laplace transform of sin h at as equal to a over s square minus a square for all s greater than a. We'll now try to find out the Laplace transform of t power k for k greater than minus 1. We define the Laplace transform of t power k as equal to integral 0 to infinite e raised to minus st t raised to k, then dt. Let's take st as equal to u, and this will render s dt as equal to du and t power k as equal to u power k over s power k. Therefore, Laplace transform of t power k is equal to integral 0 to infinite e raised to minus u, then u power k over s power k, and dt is du over s, and this is equal to 1 over s power k plus 1 integral 0 to infinite e raised to minus u power k, then du. This is nothing but the definition of the gamma function. Therefore, this is gamma k plus 1 over s power k plus 1 So this is valid for, and this is true for all k greater than minus 1. So this table shows the Laplace transform of some elementary functions, and memorizing these results will help you to calculate the Laplace transforms more easily. We'll try to do some problems with these results. The first one, find L inverse 5 over s plus 2. So we have L inverse 5 over s plus 2 as equal to 5 times L inverse 1 over s plus 2. Now recall that Laplace transform of e raised to at is 1 over s minus a. So this gives us Laplace transform of e raised to minus at as equal to 1 over s plus a. And the inverse transform of 1 over s plus a will be equal to e raised to minus at. Therefore, we can write inverse transform of 5 over s plus 2 as equal to 5 times e raised to minus 2t. And this is the required result. Find L inverse of 1 over s power a where a greater than 0. To do this problem, recall that Laplace transform of t power k was gamma of k plus 1 over s to the power of k plus 1. And this gives us Laplace transform of t power k over gamma k plus 1 as equal to 1 over s k plus 1. And from this, L inverse of 1 over s to the power of k plus 1 is equal to t power k over gamma of k plus 1. And from this, we can write L inverse of 1 over s power k as equal to t k minus 1 over gamma of k. This is the required result. We'll now proceed towards an important theorem, which is the shifting or translation theorems. In fact, there are two theorems, the first shifting theorem and the second shifting theorem. In practice, we come across many functions that are multiplied by exponential factors. Now, according to the shifting or translation theorem, if we know the Laplace transform of a function, then multiplying it by an exponential factor does not require a new computation. Let's see how. The first one is the first shifting theorem, according to which if L of ft equal to fs, that is Laplace transform of a function ft is denoted by fs, then the Laplace transform of e power at multiplied by ft is nothing but f of s minus a. Note that here fs minus a denotes the function fs which is shifted a units to the right, and hence this theorem is known as the shifting theorem. Let's try to prove this one. So the Laplace transform of ft, and this is defined to be integral 0 to infinite e raised to minus st then ft dt, and this is nothing but f of s. We'll now multiply ft with e raised to at and take the Laplace transform, and this is integral 0 to infinite e raised to minus st, e raised to at, then ft dt. And this is equal to integral 0 to infinite e raised to minus s minus at, then dt with an ft in between. And this is nothing but f of s minus a, thus proving the result. Because of the relationship between Laplace transforms and inverse Laplace transforms, any theorem involving Laplace transforms will have a corresponding theorem involving inverse Laplace transforms. Thus, we can state the first shifting theorem again as if L inverse Fs equal to Ft, then L inverse f of s minus a equal to e raised to at times Ft. So this is the first shifting theorem. We'll now try to do this problem. Show that Laplace transform of e raised to minus at t power n equal to n factorial over s plus a power n plus 1 for s greater than minus a. So we'll recall that Laplace transform of t power n was n factorial over s to the power of n plus 1. And this is nothing but fs. And this was for s greater than 0. Now, when you use the first shift theorem, we have Laplace transform of e raised to minus at t raised to n. This is nothing but f of s minus minus a, that is equal to f of s plus a. And this is equal to n factorial over s plus a to the power of n plus 1, provided s greater than minus a. Now example number 5. Find the Laplace transform of t sine at. We have Laplace transform of t sine at as equal to Laplace transform of t. We'll write sine at as e raised to I at minus e raised to minus I at over 2i. And this is equal to 1 over 2i times the Laplace transform of t e raised to I at minus Laplace transform of t e raised to minus I at. This bracket is common. Now, according to the first shift theorem, Laplace transform of e raised to at ft is equal to f of s minus a, and this gives us Laplace transform of e raised to I at ft as equal to f of s minus ia. And in this case, ft is t, therefore Laplace transform of ft is equal to fs, and this is equal to Laplace transform of t, and that is equal to 1 over s square. And f of s minus ia is equal to 1 over s minus ia the whole square. That is 1 over 2i, then 1 over s minus ia the whole square, minus 1 over s plus ia the whole square. And this is equal to 1 over 2i, then s plus ia the whole square minus s minus ia the whole square divided by s minus ia the whole square times s plus ia the whole square. When we do the simplification, then 2i, then s square minus a square plus 2i as minus s square plus a square plus 2i as over s square plus a square the whole square. There are certain terms which get cancelled. And then we have 1 over 2i, then 4i as over s square plus a square the whole square. The 2i and 4i gets cancelled. And we finally have 2as over s square plus a square the whole square, which is the required result. The next problem is to show that e raised to minus at sine bt equal to b over s plus a the whole square plus b square for s greater than minus a. We'll see how to use the first shift theorem in this case. We have L of sine bt as equal to b over s square plus b square, and this is nothing but f of s. Now, according to the first shift theorem, Laplace transform of e raised to minus at, then sine bt, this is equal to f of s minus a. And when we use this theorem, we have L of e raised to minus at, then sine bt as equal to b over s plus a the whole square plus b square, provided s greater than minus a. Another problem, evaluate L inverse s minus 1 over s square minus 6s plus 25. So we have L inverse fs, and this is equal to L inverse s minus 1 over s square minus 6s plus 25, and this is equal to L inverse s minus 1 over, we'll rearrange the denominator to be like the standard results. So this is s minus 3 the whole square plus 4 square, and this can be written as L inverse, then s minus 3 plus 2 divided by s minus 3 the whole square plus 4 square, and this is equal to L inverse s minus 3 over s minus 3 the whole square plus 4 square, which is the first term, and the second term is L inverse 4 over s minus 3 the whole square plus 4 square. So there is a 1 by 2 over here. And this is equal to, according to the first shift theorem, e raised to 3t, then cos 4t plus 1 by 2 e raised to 3t, then sine of 4t, which is the required result. Evaluate L inverse of s plus 2 over s square minus 4s plus 13. So we'll write L inverse s plus 2 over s square minus 4s plus 13 as equal to L inverse s plus 2 over s minus 2 the whole square plus 9. And this is equal to s minus 2 plus 4 over s minus 2 the whole square plus 9 L inverse. And this is equal to L inverse s minus 2 over s minus 2 the whole square plus 9. That is the first term. And the second term is L inverse 4 over 3, then 3 over s minus 2 the whole square plus 3 square. And this is equal to, according to the first shift theorem, e raised to 2t cos of 3t plus 4 over 3 e raised to 2t sine 3t. Which is the required result. We'll now discuss about the second shifting theorem. The second shifting theorem involves shifting the t variable and states that if the Laplace transform of ft is equal to fs, where ft equal to 0 for t less than 0, and if gt is the shifted function ft, that is f t minus a, then gs will be equal to e raised to minus as multiplied by fs. So this is a second shifting theorem. Let us try to prove this one. We'll start with fs, which is defined to be the Laplace transform of ft, and this is equal to integral 0 to infinite e raised to minus st, then ft dt. We'll multiply fs with e raised to minus as, and then this will be equal to e raised to minus as multiplied by Laplace transform of ft, and this is equal to integral 0 to infinite e raised to minus s t plus a, then f of t dt. And let us take u as equal to t plus a. Therefore, e raised to minus as, then fs is equal to integral 0 to infinite e raised to minus s, then t plus a ft dt. This is integral 0 to infinite e raised to minus su f of u minus a times du. And this is equal to integral 0 to a. So we have split the limits e raised to minus su, and within this limit f of u minus a is 0. So this is first term is 0 plus integral a to infinite e raised to minus su, then f of u minus a times du. And this can be written as integral a to infinite e raised to minus su. F of u minus a can be written as g of u du, and what we get is Laplace transform of gu, which is nothing but gs. So this proves a second shifting theorem. And using this theorem, let us try to evaluate the Laplace transform of the function ft, which is defined to be sine t minus pi by 3 for t greater than pi by 3 and is equal to 0 for t less than or equal to pi by 3. To do this, let us take ut as equal to sine t. So this implies ft is equal to u of t minus pi by 3 for t greater than pi by 3 and is equal to 0 for t less than or equal to pi by 3. Now we have the Laplace transform of ut as given by Laplace transform of sine t, and this is equal to 1 over s square plus 1, and this is equal to u of s. And when we use the second shift theorem, we have fs as equal to e raised to minus pi by 3 s times us, where the value of a is minus pi by 3, and this is equal to e raised to minus pi by 3 over s times 1 over s square plus 1, provided s greater than 0. So this is how we solve the problem using the second shift theorem. We'll now discuss yet another important property, that is the change of scale. According to this theorem, if fs is equal to L of ft, then f of as will be equal to 1 over a L of ft by a. So this is a change of scale property, and let's try to prove this. We have fs as given by integral 0 to infinite e raised to minus st, then ft dt. And f of as will be equal to integral 0 to infinite e raised to minus ast, then ft dt. Let's take at as equal to u, and in that case t will be equal to u over a. F of as is equal to integral 0 to infinite e raised to minus us f of u over a, then du over a. And f of as, this is equal to 1 over a integral 0 to infinite e raised to minus us f of u over a, then du. This is nothing but 1 over a integral 0 to infinite, or rather this can be written as e raised to minus ts f of t over a, then dt, which is the result. That is 1 over a Laplace transform of f of t over a. Using the change of scale property, let us show that if L of ft is equal to s square minus s plus 1 over 2s plus 1 the whole square times s minus 1, then the Laplace transform of f of 2t is equal to s square minus 2s plus 4 over 4 times s plus 1 the whole square times s minus 2. Okay, according to the change of scale property, we have L of ft equal to fs. Then L of fat is equal to 1 over a times L of ft over a. We have the Laplace transform of ft as equal to s square minus s plus 1 over 2s plus 1 the whole square times s minus 1. Therefore, the Laplace transform of f of 2t, and this is equal to 1 over 2 times the Laplace transform of f of t over 2. And this is equal to 1 over 2 times s over 2 the whole square minus s over 2 plus 1 divided by 2s over 2 plus 1 the whole square times s over 2 minus 1. And this is equal to 1 by 2 over s square over 2 minus s over 2 plus 1 the whole divided by s plus 1 the whole square, then s by 2 minus 1. And this is equal to s square minus 2s plus 4 over 4 times s plus 1 the whole square, then s minus 2, which is the required result. Example 11. Evaluate the integral ft equal to integral 0 to infinite sine xt over x dx using Laplace transforms, and hence show that ft is a step function. So we are given ft as equal to integral 0 to infinite sine of tx over x times dt. When we take the Laplace transform of ft, this is nothing but fs, and this is equal to integral 0 to infinite e raised to minus st integral 0 to infinite sine tx over x times dx, and then we have a dt. The next step will interchange the order of integration, so that this will become fs equal to integral 0 to infinite 1 over x then dx. Now in the middle we have integral 0 to infinite e raised to minus st sine of tx then dt. And this is equal to integral 0 to infinite 1 by x. When we calculate this integral, we know that this is equal to x over s square plus x square times dx, and x gets cancelled, and the integral becomes integral 0 to infinite dx over s square plus x square. And this is nothing but 1 by s over tan inverse x over a from the lookup table 0 to infinite. And this is equal to pi over 2s. So we have fs as equal to the Laplace transform of ft, or ft as equal to the inverse Laplace transform of fs, which is equal to the inverse Laplace transform of pi over 2s, and this is equal to pi over 2 L inverse 1 over s. We know that L inverse 1 over s is 1, therefore this is pi by 2 for t greater than 0. So what happens when t is negative? When t is negative, we have f of minus t equal to integral 0 to infinite sine of minus xt divided by x times dx. Sine of minus theta is minus sine theta, and therefore this is negative of integral 0 to infinite sine xt over x times dx. This is nothing but negative of ft. And what happens when t equal to 0? So in that case, we have f of 0 is equal to integral 0 to infinite 0 times dx, which is equal to 0. So we have the result for t greater than 0, t equal to 0, and when t equal to negative. For t greater than 0, the value of the function that we have calculated using the Laplace transforms is pi by 2, and when t equal to negative, the value of the function is negative of ft, that is equal to negative of pi by 2. When t equal to 0, the value of the function, that is f0, is equal to 0. Thus ft equal to integral 0 to infinite sine xt over x dx, taken as a function of t, describes a step function with a step of height pi at t equal to 0. So for the negative values of t, the function is negative, and for the positive values of t, the function is positive, and at t equal to 0, the value of the function is 0. And this function describes a step function. We'll now discuss about how to make use of the method of partial fraction to evaluate the inverse Laplace transforms. Frequently, fs, which is our transform, occurs in the form fs equal to gs over hs, where gs and hs are polynomials with no common factors, gs being of lower degree than hs. If such is the case, then there are different techniques by which we can actually calculate the inverse Laplace transform, and we are going to discuss about that. If the denominator polynomial has, that is hs, has distinct real roots, then by the method of partial fractions, we may write fs as equal to gs over hs, that is equal to c1 over s minus a1 plus c2 over s minus a2 plus the terms in between, and finally cn over s minus an, where ci are independent of s and ai are the roots of hs. To demonstrate this, let us do this problem. Evaluate L inverse s plus 1 over s plus 2. So let us assume fs as equal to s plus 1 over s times s plus 2. So this can be written as A over S plus B over S plus 2. So this is S plus 1 over S times S plus 2 equal to S plus 2 times A plus S times B over S times S plus 2. We can cancel the denominators, and now the equation becomes S plus 1 equal to S plus 2A plus SB. When S equal to 0, we have A equal to plus half, and when S equal to minus 2, we have B equal to minus 2 plus 1 over minus 2, and that is equal to 1 over 2. And from here, we have Fs as equal to S plus 1 over S times S plus 2, and this is equal to 1 over 2S plus 1 over 2 times S plus 2. That is L inverse 1 over 2S plus 1 over 2 times S plus 2. This is equal to 1 over 2 times L inverse 1 over S plus 1 over 2 times L inverse 1 over S plus 2. And this is nothing but 1 over 2 multiplied by 1 plus 1 over 2 multiplied by e raised to minus 2t. That is f of t equal to half plus half e raised to minus 2t provided t greater than 0. Method 2, when the denominator polynomial has repeated real roots. If any one of the roots, say a1, is a multiple that is occurring m times, then fs has the form fs equal to gs over hs, and this is equal to c1 m, then s minus a1 m plus c2m minus 1 over s minus a2 times m minus 1 plus the terms in between, and then c1 1 over s minus a1 and the rest of the terms, that is sum over I equal to 2 to n ci over s minus ai. To illustrate this, let us evaluate L inverse of s square plus 1 over s square plus 2. So we see that here it is s square. So fs can be written as s square plus 1 over s square times s plus 2, and this is a over s plus 2 plus b over s, then c over s square. In the next step, we will cross multiply with s square s plus 2, a over s plus 2, then s square s plus 2, b by s plus s square s plus 2, c over s square. We'll cancel these terms. To get s square plus 1 equal to s square a plus s plus 2b plus s plus 2c. This is nothing but a plus b s square plus 2b plus c s plus 2c. When we equate the like powers of s, we will get a plus b equal to 1, then 2b plus c equal to 0, and then 2c equal to 1. From here, we have c equal to 1 over 2, then 2b plus c equal to 0. This gives us 2b equal to negative of 1 by 2 and b as equal to negative of 1 over 4. And we have a plus b equal to 1, which gives us a minus 1 over 4 equal to 1. That is a equal to 1 plus 1 over 4. That is a equal to 5 over 4. Therefore, we have L inverse s square plus 1 over s square s plus 2. This is equal to L inverse 5 over 4 divided by s plus 2 plus negative of 1 over 4 divided by s plus 1 over 2 divided by s square, and that is 5 over 4 times e raised to minus 2t minus 1 over 4 times 1, then half times t. And this is the required answer. Another problem, evaluate inverse Laplace transform of 4s plus 5 over s minus 4 the whole square times s plus 3. We can see that here the polynomial repeats twice. Therefore, we'll take 4s plus 5 over s minus 4 the whole square times s plus 3 as equal to a over s minus 4 plus b over s minus 4 the whole square plus c over s plus 3. When we cross multiply the terms, 4s plus 5 equal to s minus 4 times s plus 3 a, then s plus 3 times b plus s minus 4 the whole square c. Now we'll put s as equal to minus 3. So this will give us minus 12 plus 5 equal to 49c and c as equal to negative of 1 over 7. When we put s equal to 4, we'll get 21 equal to 7b or b as equal to 3. When we put s as equal to 0, we have 5 equal to minus 12a plus 3b plus 16c, that is equal to negative of 12a plus 9 minus 16 over 7. That results in a equal to 1 over 7. So we have found out a, b and c. Therefore, L inverse 4s plus 5 over s minus 4 the whole square times s plus 3 can be written as L inverse 1 over 7 1 over s minus 4. The second term is 3 over s minus 4 the whole square minus 1 over 7 times 1 by s plus 3. This is equal to 1 over 7 e raised to 4t plus 3 e raised to 4t L inverse of 1 over s square minus 1 over 7 e raised to minus 3t. So here we have made use of the first shifting property. Also, we have L inverse 1 over s minus a equal to e raised to at. Therefore, L inverse 4s plus 5 over s minus 4 the whole square times s plus 3. This is equal to 1 over 7 e raised to 4t plus 3t e raised to 4t minus 1 over 7 e raised to minus 3t. Now for the second term we have used L inverse 1 over s n plus 1 equal to t raised to n over n factorial. So that gives us the final result. Now the third case is where there is a quadratic factor in the numerator or denominator. If one of the factors is quadratic, that is of the form s square plus ps plus q, then the numerator, instead of being a simple constant, will have the following form. That is, fs we have defined to be gs over hs. This is as plus b over s square plus ps plus q. Now, as an illustration, let us try to evaluate L inverse s square plus 2s minus 4 over s square plus 2s plus 5 multiplied by s square plus 2s plus 2. So we'll take s square plus 2s minus 4 divided by s square plus 2s plus 5 times s square plus 2s plus 2 as as plus b over s square plus 2s plus 5 plus cs plus d over s square plus 2s plus 2. Now when we cross multiply the terms, s square plus 2s minus 4 equal to s square plus 2s plus 2 times as plus b plus s square plus 2s plus 5 times cs plus d. In the next step, we'll equate the coefficients of s cube, s square and the constant terms from both sides. When we do that, we'll get a plus c equal to 0, then b plus 2a plus d plus 2c as equal to 1, then 2a plus 2b plus 5c plus 2d equal to 2, then 2b plus 5d equal to negative 4. And from here, we'll get a equal to 0, b equal to 3, c equal to 0, and d equal to negative 2. Now we can rewrite this as s square plus 2s minus 4 over s square plus 2s plus 5 times s square plus 2s plus 2. This is equal to 3 over s square plus 2s plus 5, then minus 2 divided by s square plus 2s plus 2. In the next step, we'll take the inverse Laplace transform on the left hand side of this equation. This is equal to the inverse Laplace transform of 3 over s square plus 2s plus 5 minus the inverse Laplace transform of 2 over s square plus 2s plus 2. In the next step, we'll rearrange the denominators. So this is 3 over s plus 1 the whole square plus 2 square minus L inverse 2 over s plus 1 the whole square plus 1 square. And now we are in a position to apply the shift theorem. So we'll take out this 3 and this is e raised to minus t multiplied by L inverse of 1 over s square plus 2 square minus 2 times e raised to minus t and L inverse 1 over s plus 1 s square plus 1 square. And this is equal to 3 times e raised to minus t cos 2t minus 2 e raised to minus t cos t, and this is the required answer. If ft is continuous for t greater than or equal to 0 and its first derivative, that is f prime t, is piecewise continuous in every finite interval t between 0 and k, and if mod ft is less than or equal to m e raised to bt, that is ft is of exponential order, then the Laplace transform of the first derivative of ft, that is f dash t, will be equal to s times the Laplace transform of ft minus f0 provided s greater than b. And this result can be extended for the nth derivative of ft. For the nth derivative of ft, that is f nt, the Laplace transform will be Sn Lft minus Sn minus 1 f0 minus Sn minus 2 f prime 0 and the terms in between, and the final term will be Fn minus 1 0. We'll skip the proof which could be found in this book, Mathematical Methods for Physicists, A Concise Introduction by Kai-El Chow. We'll now try to solve the ordinary differential equation with constant coefficients using this technique. Solve the differential equation y double prime plus 9y equal to 0, satisfying the initial condition y0 equal to 0 and y dash 0 equal to 2 using Laplace transforms. So here we have y double prime plus 9y equal to 0. In the next step, we'll take Laplace transform on both sides, that is Laplace transform of y double prime plus 9 times Laplace transform of y equal to Laplace transform of 0. So that gives us Laplace transform of y equal to 2 over s square plus 9. and this is equal to 2 over 3 times 3 over s square plus 9. And y is the inverse Laplace transform of 2 over 3 times 3 over s square plus 9, and this is equal to 2 over 3 times sine 3t. So this way we can find the solution of ordinary differential equations using Laplace transform. Finally, we'll discuss how to calculate the Laplace transform of functions that are defined by integrals. If gt is defined to be an integral, that is integral 0 to t fu du, and if fs is equal to the Laplace transform of ft, then the Laplace transform of the integral function gt will be equal to fs over s. And similarly, if L inverse of fs is equal to ft, then the inverse transform of fs over s will be equal to gt. So this is how we can calculate the Laplace transform of integrals. As an example, let us compute the Laplace transform of integral 0 to u sine au du. Let us take gt as equal to integral 0 to u sine au du. So this is integral 0 to u fu du. Now the Laplace transform of an integral function is L of gt. So this is equal to Laplace transform of f of u over s. And this is equal to the Laplace transform of sine au over s, which is 1 over s times a over u square plus a square. Thus, we can calculate the Laplace transform of an integral function. So with that, we conclude this video, and in this video we have learned about Laplace transforms, its properties, and how to solve partial differential equations and integrals using Laplace transform technique.